Hey everyone, my name is Wang. Today I'll explain a method for encouraging pro-social behavior in environments with multiple selfish learning agents. So specifically, we're trying to learn correlated equilibrium using a synchronized exploration method. So reinforcement learning methods have become really successful recently in training agents to solve human relevant tasks. Specifically, deep Q networks and policy gradient methods have shown enormous success in single agent environments. However, multi-agent environments are still a challenge. So when multiple learning agents are present, the environment becomes non-stationary for each agent, and learning when to cooperate versus compete can be difficult. So we take a look at multi-agent RL from a game theoretic standpoint. We want to maximize the social welfare while still having selfish agents. So to illustrate these concepts, we'll examine the iterated game of chicken. In the game of chicken, each agent can either chicken or dare, and the game has two agents that are in collision course, and neither wants to be the one that swerves and chicken out. But if both dare, they will crash, which is undesirable. Each turn, the row and column players simultaneously select their actions and receive rewards according to the payoff matrix shown. And one solution concept is the pure Nash equilibrium, in which each agent has no incentive to deviate from the strategy given the strategy of their opponent. So there are two pure Nash equilibria. One of them is such that the first agent always chickens and the second always dares. And the second is such that the first agent always dares and the second always chickens. So these are the two pure Nash equilibria. And although these are good predictors of rational behavior, there's just a more general notion of equilibrium that still maintains rationality and allows for better social outcomes, namely correlated equilibria, which is a superset of the pure Nash. Correlated equilibria is any randomized action recommendations that no party wants to deviate from. So the correlated equilibrium is pro-social as it can achieve a larger expected sum of agents reward compared to the pure Nash equilibrium. So here's an example of one such correlated equilibrium in the chicken setting. So we consider an oracle that at each turn sends each agent a signal that encodes the recommendation. Each agent only observes their own signal, but the oracle correlates the two signals. So one example of a correlated equilibrium is when the oracle draws one of three pairs of recommendations and gives them to the agents. So with probability 0.5, the oracle recommends both agents to chicken. With probability 0.25, the oracle recommends dare chicken. And with the final probability of 0.25, the oracle recommends chicken dare. And under the action recommendations of the oracle, no selfish agent would choose to deviate. So the pure Nash equilibria are easier to learn as they only require one agent to selfishly always choose dare, and the other agent's best option is just to chicken all the time, assuming the daring agent won't change their strategy. But correlated equilibria are harder to learn as the agents must both accept the action recommendations of the oracle. And suppose the agents are in pure Nash, as in the matrix shown. By definition of pure Nash equilibria, neither agent has incentive to deviate, so individual exploration would not be as effective in changing either agent's strategy. However, if agents explore together and try exploratory actions at the same time, there's higher chance they might perform actions necessary to reach correlated equilibrium. So synchronizing exploration of agents increases the probability of performing actions that lead to correlated equilibria. So I'll describe our method. As a quick refresher, here's regular epsilon greedy exploration, where each agent independently explores. Each agent independently with probability epsilon selects a random action, and with probability 1 minus epsilon chooses its current best action. And here's our method of synchronized epsilon greedy exploration, where both agents explore or act greedily based on a shared epsilon parameter. So this method encourages exploring correlated equilibrium actions together and allows agents to retain self-interest in the long run. And unlike previous methods, such as correlated Q learning, agents don't need to share the details of their policies with each other. And also our method can be applied to any algorithm that allows off-policy exploration. So we test our method by using synchronized exploration with DQN, and we compare our method to various baselines. And from this graph, you can see average reward is on the y-axis. So as one baseline, we use MAD DPG, which encourages cooperation via centralized training, but we can see here that it reaches pure Nash equilibrium. We also try reinforce, which also reaches pure Nash. And we tried vanilla DQN with independent epsilon greedy exploration, and that reaches pure Nash. But our algorithm reaches correlated equilibrium as we want. And so we found that random initialization has a large effect on how often each method reaches correlated equilibrium. So we use 100 different runs for both DQN methods with varying initializations, but the same hyperparameters. And we can see that synchronized epsilon greedy results in correlated equilibrium for more runs with varying initializations. But independent epsilon greedy has more runs that start out in correlated equilibrium, but very few that end up staying in correlated equilibrium after training for a while. And so our work is still very much a work in progress. We're working on evaluating our method on more general stochastic games. And we've already designed our own new game called Grandma's Cookies as an extension of the iterated game of chicken. We're also investigating a frozen exploration approach where the agents take turns making optimization steps and exploring. And the idea behind this is if the frozen agent can fix an exploratory strategy, then the learning agent can hill climb and learn the best current strategy with less stochasticity from the environment. And finally, we're considering methods to explicitly condition the policies on the signal, as preliminary results show it's pretty difficult to force the agents to consider the signal. So yeah, that's it. Thanks for listening.
Awesome. Thank you for the talk, Woody. So we have one question from Slido, actually. This person is asking, how will the agents know that they should both explore? Is there some mutual signal?
Yeah, so the way we're doing this is basically like at the beginning of training, the synchronized exploration has a shared epsilon. So it's just like they both have to explore at the same time or act greedily at the same time. And then that epsilon is annealed and decays to where they can act selfish in the long run. But like at the beginning, they coordinate in their exploration.
Sounds good.